shell structure analysis report. To digitally find the form-finding model, I use Kangaroo. The model of the perspective axonometric views are shown. The top view can be seen here, showing the dimensions. Model is 0.5 meters by 0.3 meters. The elevations and sections are shown. The elevations reveal that the lowest droop of the fabric is 0.05 meters and the smallest is 0.08 meters. My model is based in Canberra in the city forest. The average snow load is 0.784 kilonewtons per meter squared and the average wind load is 1.226 kilonewtons per meter squared. The physical form finding model fabrication process. Materials that I used included wood, hooks, 4-way stretch fabric, and zip ties. The first step was to cut a piece of fabric 50% larger than the base of the model. Step 2, I measured out the supports on the wood base and drew support points on the fabric. Next, in step 3, I screwed the hooks onto the wood and attached the zip ties at the support points. In the final step, I hung the zip ties to the hooks, revealing the form-finding model. The final model had the same dimensions, 0.5 times 0.3 meters. Reflecting on developing the physical form-finding model, I found using hooks and zip ties was most effective, as it allowed precision and accuracy, ensuring that the final model closely resembled the intended design. This also eliminated having to try and tie the string to fabric. However, one issue was the uneven cutting of fabric, resulting in excess material and irregular edges. This lack of precision may have introduced unintended distortions and imperfections. Overall, the final model provided the behavior of the material under tension, representing the form-finding model. Comparing the results of the digital and physical form-finding models revealed both similarities and differences in the overall shape of the structure. The digital model represents smooth and uniform appearance, with curves that closely adhere to base dimensions. In contrast, the physical model exhibits small folds and excessive fabric. There is a discrepancy of the models when simulating fabric behavior. In the digital model, the fabric is allowed to droop while maintaining its original size. However, in the physical model, the fabric was enlarged by 50% to induce drooping, which led to folds. The digital model offers efficiency and flexibility in exploring various support points and configurations, allowing for rapid iteration and visualization of design concepts. The physical model provides a tangible representation of the structure, offering insights into real-world behavior and highlighting the practical considerations that may not be evident in the digital realm. I then created a wireframe model by baking the mesh. These are the perspective and axonometric views. The top view is represented, showing the dimensions of 0.5 meters times 0.3 meters. The elevations and sections of the wireframe model are shown, revealing the same dimensions previously of 0.15 meters. Structural analysis and optimization was done using Karamba. This is the data shown for just the gravity load. The load reaction is shown, revealing the direction and amount of force. The cross-section was 0.6 centimeters, with the material being concrete. The utilization was shown at 80.6%, revealing displacement and stress data. I then applied the snow load. This shows that the reaction force of the load increased by 0.01. The cross-section was 0.8 centimeters and the material used was concrete. Again, the utilization was at 80% and the data for displacement and stress decreased. These results reflect the increased load. The wind load was then added. This increased the reaction force by 0.02. The cross-section was 1 centimeter with the material being concrete. The utilization was at 80.1% and the displacement and stress both decreased again. These results again reflect the load being increased. The 3D model for fabrication was created. Here's the perspective and axonometric views. The dimensions are revealed on the top view. These dimensions are the same as the previous wireframe model. The elevations and sections reveal the dimensions. The thickness of the model is 1.03 centimeters. The physical structural model, failed attempts and testing. My initial attempt involved using a 4-way stretch fabric combined with plaster cement. However, these materials proved unsuitable. Upon drying, the plaster crumbled, lacking the necessary strength. Furthermore, the fabric failed to effectively absorb the material, causing the plaster to disintegrate. I also experimented with concrete and cement, but they too lacked strength due to the inadequate absorption of the material. In my final attempt, I then changed to a more absorbing fabric, cotton, and used mortar, which is composed of cement, fine sands, and lime. To create the final model, I used materials wood, hooks, cotton fabric, zip ties, and mortar. Step 1. cutting the cotton fabric 50% larger than the base, then making the support points. After that, I mark the support points on the wood slab base. Step 2. Screw hooks to the wood slab where the support points were marked, then adding zip ties to where the support points were marked on the fabric. Step 3. Set the wood base with hooks hanging downward. Dip the fabric in water, saturate it in the mortar, then hang up the zip ties that are attached to the fabric into the hooks. Step 4. Let the structure dry, then cut the zip ties and let the structure stand right way up. I then did a load test on the physical model. To do this, I converted the snow and wind loads from kilonewtons per meter squared to kilograms. The snow load was 12 kilograms and the wind load was 19 kilograms, which meant that the model should be able to hold up to 31 kilograms. However, during the load testing, the model could only withstand a threshold of 19.1 kilograms. The dimensions were the same for the width and length, but the heights were smaller than the digital model. When developing the prototype, I gained knowledge of the properties of different materials. I learned the characteristics of concrete, plaster, cement, and mortar, and their respective strengths and weaknesses. Plaster cement, despite its ease of use, proved to be inadequate due to its softness and slow drying time. Concrete exhibited poor adherence to the fabric and was too thick, leading to challenges in application. Mortar was the most suitable option. Its fast-setting nature and fine consistency allowed for effective bonding with the fabric. I found cotton fabric, while more absorbent than four-way stretch fabric, presented challenges such as creasing and curling along the edges. Despite these challenges, I am pleased with the strength and shape of the model. The use of mortar proved effective in achieving structural stability and overall form, successfully capturing the intended design concept. Comparing the outcomes of the digital structural analysis in Karamba. In the model, the expected load capacity was set at 30.7 kilograms. However, during the physical load test, the physical prototype could not withstand a maximum load of 19.1 kilograms before experiencing a slight inward collapse along its edge. Several factors contributed to this disparity. Firstly, the presence of creases on the fabric surface weakened the strength of the model, creating points of vulnerability under load. Additionally, inconsistencies in the application of mortar across the fabric surface further compromised its strength. Variations in pressure distribution on supports attributed to their imperfect alignment with the ground introduced uneven loading conditions that impacted the prototype's ability to withstand applied forces. The inability to uniformly distribute load across the model also contributed to the discrepancy between the expected and actual load capacities.